Okay, so we have also discussed about the propagation properties here of the waves. So this is the speed of propagation. For example, this kx omega t is a constant. Okay, and this wave function, we see that this ym is the amplitude sinus kx minus omega t. Okay, this minus sign means that the wave propagates from the left to the right. Okay, with the speed is greater than 0. And for the second function, we have this plus sign here. It means that the wave moves from the right to the left. Okay. So we have also discussed that the speed of the waves depends on the medium. Yeah? This is, for example, for string waves. Okay, we have discussed. Okay, these string waves, and the velocity depend on the mass density of the string and also the tension of the string. Okay, the square root of the tension over the mass density of the string. So we have this one, okay, and this is the power of the waves. Yeah, it means that every wave phenomena, it means that the energy propagates through the via the waves. Okay. So because so let me discuss this one. Okay. So because the power of the waves, okay, is this one, okay, and in general it depends on x and t, okay. So we get that this power depend on x and t, this one, sinus square of kx minus omega t, okay. So because the square here, so it means that everything is positive. So this is the definite positive function. Okay. So because this depends also on the position and the time, for example, we have to choose x. Okay. For example, usually we get this x is at the region, this x equals 0. And then we average the power here, the average power with respect to the time, okay, to one period, okay. So we get that this sin square is a half the square, the average. So we get the average power of the waves is half mu, this mass density V, and also omega squared S squared, okay. So it means that the energy of the waves depend on density, the mass density of the string or the medium, the propagation wave, the speed of propagation waves, and then this angular frequency squared and the amplitude squared. Okay, so this is power in classical waves. So the energy, average energy per length is equal to this one. Okay, we have discussed. Okay, we have discussed here. We have discussed here. Okay, so this is the superposition. Okay, what happened if we have two or more waves here? It could be superposition phenomena. Superposition phenomena. So it means the superposition we add these two waves. We can add this, for example, this psi1 and psi2. So what happened, for example, if we have the same phase, but different propagation, the propagation direction, okay, you see that this the amplitude will rise, okay, will become bigger, okay, and then they split again. So this is the simulation, okay. With the dash here, is the original amplitude. Yeah. Okay. So this is the constructive interference, in constructive superposition. They become, the amplitude become bigger. So this is the, for example, the superposition, yeah, okay. So this is destructive in superposition, and then there is constructive superposition. Okay, so it means that the superposition we add two wave function. Okay, this one. So although we add these two wave function, it means that we do not change, yeah, the direction of the propagation of the waves. Okay. So why superposition works? Because the wave equation is a linear equation. Okay, so because it's linear, it means that if we have two solutions, we could add it, we could sum it. We could sum of all solutions. Okay, because we have linear wave equation. So we have also discussed about Phasor diagram. Phasor diagram. Okay, this A0 here is the amplitude, okay, maximum amplitude. Okay, so E1 here is the wave function. Okay, so there is a phase here, omega t, okay. If they have, for example, this is E1, for E2, for example, it has the same amplitude, but it has different phase, okay, this phi here. So this is the Phasor diagram of two waves. Yeah. So this is the superposition. Okay. This ER is the resultant waves. Okay. So in general, this ER here, the wave function is EP. Yeah. This EP is ER sinus usually Kx minus omega t plus alpha, where alpha is the phase difference. Okay. So there is how many? 1, 2, 3, 4. Okay, there is 4 waves. Okay. So this is the resultant amplitudes. Okay, and this is the wave resultant. Okay, we get this EP equals to ER sinus omega t plus alpha. Okay, this alpha is the phase difference between the first one and this resultant waves, okay, the resultant amplitudes. So this is the interference, okay. So we have here, if we add these two wave function, okay, we get this equation, okay. We have this wave function, okay, and we have this one, okay. So this is somehow the amplitude function in the sense that this amplitude is no longer, let's say, a constant, but different on phi. Okay, phi is the phase difference. So what we get that constructive mean we have the maximum value of cosinus. Okay, so cosinus we have 1 here if is the multiplication of 2 pi. Okay, so phi should be 2 pi n. Okay, that's the constructive. Yeah? We could also have this minus, okay, this minus 1, okay, but in general, we could have +1 or -1, okay. Destructive means this cos phi over 2 is, the cos of this phi over 2 is 0, okay. It should be n plus half times 2 pi. This amplitude plus minus 2 yn for maximum, constructive. So this is, for example, yeah, we have two identical waves, yeah, who moves in the same direction, okay, but they have different phase, okay. So what happened if we sum of this y1 and y2 with y2, we get this resultant waves, okay. If phi is pi over 2, okay, we get that this phase here, sorry, okay, this is cos pi over 4, okay, this is basically 1 over square root 2, okay. So we get that this A here is 1.5 ym. Okay. So this is constructive interference, and this is destructive interference. Okay, they have different phase. Okay, pi. The phase difference is pi. Okay. What does it? The physical meaning of this superposition interference? So interference can be viewed as the superposition of two or more waves function. Okay. So, for example, if we have this omega 1 and omega 2, yeah, if we take that omega 2 is 1.15 times omega 1, okay, this B here. So how about this superposition? The waves function looks like this, okay? This is the minimum here. We call it this destructive interference because we have the smallest amplitude, yeah, near zero, and then this is the maximal interference or constructive interference, okay, because the amplitude is the constructive interference, okay. So this function we call it beats, okay, beats, B-E-A-T. Pelayangan in English it beats. Yeah. Okay, so we have this for these beats, we have this lower frequency, and this is the higher frequency. Okay, so this is the simulation. Okay, these beats we have discussed, I think last week. So this is the reflection of the waves. Okay. So for example, for fixed n, yeah, in the left we have fixed n. Okay. The reflected waves will have the phase difference is pi. Okay. For fixed n. For free n, okay, free n, we get the same phase, okay, the reflected waves. This is, for example, this bolt here, the mu, the mass density is greater than this thin, okay? This thin string, okay, this bolt string and the thin string. It means that, for example, if the incident waves coming from this thin string, yeah, okay, they will have reflected and transmitted wave, okay. This is called transmitted wave, this one. Okay, the amplitude will decrease, okay. Okay, and also this one from this denser mass density, okay. Sorry, problem again with this Zoom. Not the connection, I think that's not gonna, is problem with the Zoom, I think. Hello, anyone can hear me? Hello? Hello, anyone can hear me? Hello?
Yes, I can hear you. Hello.
Halo, halo, ya. Anyone can hear me?
Sudah
Halo?
terdengar, Pak.
Okay, good.
Loud and clear, sir.
Okay. Okay, we already discussed this last week. Yeah? And also there is standing wave, okay, standing wave. So they have, for example, the same phase, yeah, but different propagation, okay. For example, this is from the left to the right, and this is from the right to the left, okay. If we add these two waves, okay, using this property of sinus, okay, we will get the spatial term will split into this temporal term, okay, this time term, okay, and this is the time term, and this is the temporal term, okay. So the amplitude of the standing wave depends on the position. This is it is not propagating waves. Okay. So this is the standing wave. Okay, you see that there is constructive interference, constructive superposition or destructive superposition. Okay. So in the standing wave, we call it nodes. Nodes is a point with zero amplitude. Okay. So it means that if this is zero amplitude, the sign here, it should be the multiplication of n pi. Okay, where n is 0, 1, and 2. This kx should be equals to n pi. And we get that this x here is n lambda over 2. Okay, because k is 2 pi over lambda. For antinodes, antinodes is a point where the amplitude is maximum. Okay, so sin kx it should be multiplication of pi over 2 or 90 degrees. Okay, so it should be like this. So we will get this one. Boundary condition. Okay, on the standing wave. Usually for fixed n, we have a node at the end. Yeah, that reflected. We have different phase. Okay, for free n, we get antinode at the end. Yeah. And the wave have the same phase. Yeah, the same phase. So this is, for example, for fixed n. Okay, fixed n means fix, ya, ujung terikat, tetap, ujung tetap, atau fixed n. So this is the boundary condition. At the left end, we have x, we have y, x equal 0 is 0, yeah, and this x equal L is also 0. Okay, so sin KL equals 0, it means that KL is equal to n pi. Okay, so we get that this K is n pi over L, where n is 1, 2, 3, and etc. So we get that this lambda is 2L over n. Or we get that, for example, this F here is NV over 2L, okay, where V is square root this string tension. Hello, hello? 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 Hello, can anyone hear me? Hello? Hello? Hello?